Hello class, welcome to Algebra Lesson 3.6, which is all about scatter plots and lines of fit. By the end of this lesson, you should be able to find a line of best fit for a data set and evaluate the goodness of fit. So let's look at example 1. Find the line of best fit. So what is the equation of a line that is the best fit for the data in the table? So yesterday we talked about trend lines and how you can pick two kind of points, whether they're existing data points or 2 points that just kind of lie in the middle of your data. That gives you a line that kind of cuts through your scatter plot, right? It gives you like half the points above, half the points below. So what we're going to do today is we're going to learn about a tool that you can use so you're not doing that all by hand anymore. So this tool that you can use is called a linear regression model, and there's actually an online calculator that I'm going to have you use in order to find that information for you to make your life a little bit easier, okay? So what I'm going to do is all of those points that are on the screen right now from this XY table, I'm going to input those into my online linear regression calculator, and I'll link to it in our Google Classroom so that way you can use it too on your homework. And I'm going to show you what kind of information it gives us. Okay, so what I did was I plugged all of those points into our linear regression XY table. And like I said, there's a link in Google Classroom that will bring you to this page. And so I typed in all of those points, and then what it gives you is a little box that looks like this. Okay, so on this graph, it's going to tell you it has the Y1, and then we have our MX1 and our B. What I need you to focus on is actually our parameters at the bottom here. These parameters are those values you need to write your equation. So M still represents your slope, so you'd say Y equals 13.56 X, and then B is still your B value, so that way it does the slope-intercept form for you. And often with these, we actually will not round. We'll usually use several decimal points when we're doing this kind of work. Okay, so all I did was type in those XY points, and then once I typed in those XY points, it found this line of best fit for me. Okay, so I'm going to erase that quickly, and I am going to go back to Smart Notebook. So you can say that the equation would be Y equals 13 points, what was it? It was 5.6, if I round 5.6 X plus, and then it was like 17.59. And that would be my equation. So all I had to do was plug those points in. Now I want you to try it on your own. Here are your X and Y values. I want you to plug them into that online calculator. Look for your M value, your B value, and write your slope-intercept equation for this table. Good luck. Okay, hopefully the equation of the line of best fit that you got was 0.78x plus 4.69. Now let's move on to our next example. So understand correlation coefficients. So what does a correlation coefficient reveal about the quantities in a bivariate data set? You might be thinking, Ms. Johnson, you just said a lot of words that I have no idea what they mean, and that's okay. All right, so a correlation coefficient is something that graph or the place that you put your XY table into, the correlation coefficient is another value that's represented. So R represents your correlation coefficient. So this is something that, again, that online tool is going to help you find the correlation coefficient. Now, what a correlation coefficient means is what it tells you is how closely your line matches all of the points on your scatter plot. So let's say that you had a bunch of points that were in a straight line. okay? A nice straight line. You could draw a line of best fit that would go through every single point. That would be a strong correlation coefficient. That means that the line, if I plugged in any number into that equation for that line, I would get an answer out that is very accurate. However, in real life, that doesn't happen super often. Like once you start getting into things like with business and predictions or things like that, you can't always have a perfectly exact line. So the correlation coefficient tells you how reliable your line is. And what bivariate data is it's just a set of data that uses two variables. So all of those points that you plug in, so all those points on that XY table, that's considered bivariate data set because you had an X value and a Y value. Okay, so a big, long, kind of new name for something that you already know how to work with. Okay, so let's talk about how to tell when correlation coefficients are good predictors and when they're not. So if we look at this first graph here, this correlation coefficient, that R value, is 0.984. Do you see how that's really close to the positive number 1? That tells me that this line of fit is really accurate. Okay, so that means that's a reliable equation to use to predict things for the future. If I look at this second graph here, you can see how the line only touches one point and everything else is kind of scattered, right? If I look at the R value, it's negative 0.284. So the farther an R value is away from either a positive one or a negative one, means the weaker the correlation coefficient is. It means that that line becomes not so trustworthy. So if your R value is close to 0, your correlation coefficient is not great. That means that that line cannot really be used to predict, cannot really be used to predict a future value. And then when we have a correlation coefficient that's close to a negative 1, that's actually really good too. That tells us that there is a strong relationship between our X and Y values. It's just that it's a negative relationship. So the closer it is to a positive 1 or a negative 1, means that it has a strong relationship. If the R value is close to 0, there's not really a relationship between the two. All right, so what does the correlation coefficient reveal about the data it describes? What would you say about an R value that's 0.1? Go ahead and take a second to think about that. Hopefully you said that would be a weak correlation coefficient, and you could also say that it's a weak positive, right? Because it is a positive value that was listed. What would you say about an R value if it equals negative 0.5? Good luck. Hopefully for this one you said, okay, 0.5, that's like at a halfway mark. So I'd call that maybe like a medium. And then it's a negative 0.5. So I'm going to say it's a medium negative correlation coefficient. Okay, so that medium means that it kind of has a relationship between the two, but it's nothing too strong. It's not the best, not the worst. Now, let's talk about another vocab word. So this vocab word is residual. And what a residual is when you take those actual points on your graph, so all of those red dots, and then you figure out how far away are those points from the line. Okay, so the way you find a residual is you take the actual value that's listed in your XY table and you subtract whatever your predicted Y value is. So when you plug something into an equation and you get a different value, that is called your predicted Y value. Okay, so you do your actual from your table minus your predicted, and then what you do is you can plot those. So like if we look at the value, this very first one right here, the point is at 2, looks like 2, 2, but our graph is maybe at like 1.5 or something. So you would say, how far away is our actual y value, which was 2, minus, so here was my actual y value, minus my predicted y value was 1.5. So that's 0.5 units away. So when x equals 2, it is 0.5 away from the actual value. My line is 0.5 units away from the actual. So then what you do is when x equals 2, you go to x equals 2, then you go up to about 0.5 and you plot a point. Then you do the same thing. Like here we have 3. When x equals 3, our value tells us that it's a 4, but our line tells us it's maybe like 3.25 or something. So then they would be about 0.75 units away. So when x equals 3, my y value is 0.75. So that's how they're plotting these points. This is called a residual graph. Okay? And what this does is it tells you how well a linear model fits the data set. Okay, so if those points are randomly located on either side of the x-axis, so some above, some below, and they are close to the x-axis, the linear model is considered to be a good fit. The farther away those points are from the x-axis, the worse the fit is. Okay? So, example 3, let's talk a little bit more about residual plots. Student enrollment at Blue Sky Flight School over 8 years are shown. The owner used a linear regression to determine the line of best fit. The equation for the line of the best fit is y equals negative 35x plus 1,208. How well does the linear model fit the data? So whenever you're trying to figure out how well the linear model fits the data, you're going to use a residual graph. So what they did in this table is they have their x values, their y values, and then they used their linear equation to do our predicted value. And then the way that they got their residual was they said actual, so 1,235 minus 1,208, and that equals 27. They did the same thing for each of these. 1,115 minus 1,138, that's a negative 23. Okay, so they just kept going across. They'd say this minus this equals this. And they just did that. And then what they do is they graph those points. So 1 goes with 5, 2 goes with negative 23, 3 goes with a negative, I think that was a 1. Yeah, negative 1. And they plotted those points on the residual plot. The x and y values were also used to make this graph, and the line of best fit was drawn in on the enrollment graph. Okay, so we have our enrollment graph with the actual points, our line of best fit. Then we have the residual plot to help us determine if it was a good fit. So if we look at this residual plot, we can see that it shows the residuals, so all of those points are randomly located above and below the x-axis, right? There are some above, some below, and they are clustered close to the x-axis, okay? So when we're looking at points that we're going anywhere from just above like 20 all the way down to like maybe almost a negative 50. But when your values are in the thousands, that's not too far off. So having those values be, even though they're not right next to 0, overall, they're pretty close considering we're talking about numbers that are in the thousands. So this would be considered a good residual plot that tells us that the linear model is likely a good fit for the data. And you can kind of see that if you look at your graph, because the line basically hits every single point that was plotted on that graph. Okay, let's talk about example 4, interpolate and extrapolate using linear models. And you're probably thinking, wow, Ms. Johnson, you're throwing so many big words at us today. I am, but I know you can do it. So we have the graphic shows regional air travel data recorded by a domestic airline company. How can you use the data to estimate the number of air miles people flew in 2003? If the trend in air travel continues, what is a reasonable estimate for the number of miles that people will fly in 2030? Okay, so you can see, instead of setting it up in a boring traditional XY table, they did it on a picture of a plane, because why not, right? So time is always going to be your X value, so year is our X value, and then air miles traveled is our Y value. Those all represent in thousands, okay? And then what we are going to do is we're going to plot those points. So you can see, took all of those points, put them on a graph, and now what I'm going to do is I'm going to plug those X, Y points into that online linear regression calculator to see what kind of information I get out. Okay, now that I plugged all of those values into for my XY table, for the years, I just, instead of typing in like 1975, I just did 0 because that's where we were starting. And then I did the number of years after that starting year. So like our first one was 1975, I put a 0. And then the next one would be 1980, so that's 5 years later, and then 10 years later, 15, 20, 25, 30, 35, 40. Okay, so I did that just to make my numbers a little smaller, more workable. And then for the Y value, I just plugged in the numbers that they gave me. Once I did that, I got my lovely parameters, which allows me to write an equation. So my slope is 47.87 and my y-intercept is 1,345.04. So I'm going to go back to my graph, and here is my equation all typed out. That is the equation I can use to predict. Okay, so now that I have that equation, let's talk about interpolation versus extrapolation. So interpolation is using that model, so that equation, to estimate a value within the range of known values. So the question asked, estimate the number of miles people flew in 2003. Well, we have information from 1975 all the way through 2015. So 2003 lands between those 2 years, so that's why this is considered interpolation. It is between the given X values. So all we have to do is figure out, okay, how long after 1975 was the year 2003? Well, it's 28 years later, so I can plug that in for my X value. So I have 47.87 times 28 plus 1345.04 to get a total of 2,685.4. Okay? Extrapolation is outside of the range of values. So again, we had information from 1975 all the way through 2015, but if I look at the year 2030, that comes after 2015, which was my last known data point. So extrapolation is when you pick something outside of your range of X values and plug it in. So 2030 is 55 years after 1975, so I'm going to plug that in for X. So y equals 47.87 times 55 plus 1,345.04 for a grand total of 3,977.89. So you can write a little summary if you would like. The model predicts that the people flew a total of 2,865,000 air miles on the airline in 2003, and that people will fly a total of 3,978,000 air miles in 2030. So this prediction is not as reliable as the estimate for 2003 because that trend could change, right? Especially if you even think about our current state in the world with the pandemic. With the pandemic, flights went down, right? There were not as many people flying. So this model would not be necessarily accurate even for the year 2020, just because the pandemic came into play. And there are always things that can impact a trend. So it's important to think about those as you're making predictions for the future and realize that that's all it is. It's a prediction, and it might be accurate, but there also might be something that happens that causes it not to be accurate anymore. Okay, so using this model, estimate the number of miles people flew on the airline from 2012. Good luck. All right, for your answer, hopefully you figured out that 2012 is 37 years after 1975. So you plugged 35 in for X, and when you did that, you got 1,771.19 plus 1,345.04, and that left you with 3,116.23 thousand air miles, because remember that was our label, or if you actually want to convert 3,116.23 thousand into a number that you're familiar with, you could do 3,116,230 miles. Both answers are correct. I would accept either one. All right, let's talk about our last example for today, correlation and causation. So our first situation that we're going to talk about is a student found a positive correlation between the number of hours of sleep his classmates got before a test and their scores on the test. Can he conclude that he will do well on the test if he goes to bed early? Okay, so here's the information that he gathered. He plotted points of how many hours his classmates slept and how well they did on the test. But do you think that's a realistic thing to predict? Is hours of sleep going to impact test score? Is it the only thing that impacts test score? Well, if you think about it, let's say you don't study for a test and you're just like, you know what I'm going to do? I don't need to study. I'm just going to go to sleep and get 8 hours of sleep before the test, and I'll do just fine. How would that work out? It might go okay, but if you didn't study or anything, chances are that test, it doesn't matter how long you sleep before it, you're not going to do well on that test. So this is an example of, like, if you think about causation, okay, so you guys are familiar with like cause and effect, okay, so causation describes a cause and effect relationship. So a change in one variable causes a change in the other. So a change in the hours of sleep, does that necessarily impact a test score? No, because like we said, if you didn't study, chances are you're still not going to do well, okay? So this first example is not considered a causal relationship. In order for two things to have a causal relationship, you have to be able to control other variables that impact the relationship. So you'd have to control exactly how many hours each person studied. Like, you'd have to make everything else consistent so that way hours of sleep was truly the only thing impacting test scores. Okay. Then a lifeguard notices that as the outside temperature rises, the number of people coming to the beach increases. Can she conclude that the change in temperature results in more people going to the beach? Okay, so let's think about that one. At least in Minnesota, this is probably pretty true, right? As the temperature rises, more and more people go to the beach. But what if we're somewhere else? What if we are, let's say, like down in Florida? We're by the ocean. Other things could impact that, right? Not only the weather. I mean, it could be warm. I guess this one would apply to Minnesota. It could be hot out, but what if it's storming? There aren't going to be as many people at the beach. So the change in temperature isn't the only thing that impacts the number of people at the beach. So this would be another example of this is not a causal relationship because it's not the only thing that impacts the temperature is not the only thing that impacts the number of people at the beach. And if you were talking about like down in Florida, it depends on the time of year, right? Because around that spring break time, a lot more visitors go down there. And if it's visitors from Minnesota, chances are it's significantly warmer down there. So you guys are all willing to go to the beach and go swimming. But maybe people from Florida are like, it's still too cold for that. So the season definitely impacts how many people are at the beach. Okay, so there are multiple things. There's the weather, there is the season. It's not just the temperature that impacts the number of people going to the beach. Okay, so here's a little concept summary for today. If you have questions about anything at all from this lesson, please don't hesitate to reach out for some help. I am more than happy to help you. Have a great day.